posted the calendar.
But on the 11.1, I couldn't get the second last problem in the second.
No, I didn't make it. Yeah.
The angle, that's the
So,
one.
I don't know if you can show me black prayer.
Every time I would do practice another, I would charge right here.
I should get I should
Honestly, I would not get data. The subject was that's raised out. That's like at least 6 years ago.
Especially because like what was I just doesn't make sense. Instead of I have.
If you use a convenient I instead of I.
Okay, let's see if we can do the lights again. You don't know what button you hit. Oh, wait, there we go. Well, let's go ahead and start. So last time we left off with this concept that if we had two vectors that sat here, I don't remember which one was A and which one was B, but we'll say that one was A and B, that we could figure out how to find the projection of A onto B using a dot product. I'm going to take, I wish I had made that smaller, but I'm going to take this idea and go a little further with it. But before I do that, I don't think it's very much of a stretch to go into 3D from 2D. Okay, you've got different coordinate systems you can get. And so I guess what we got to do is start thinking about this. If this were X and Y, then you take your hand, point it in the X, swing it to the Y, and your thumb would go into the Z. But if this were X and Y, you'd swing that, and it would come towards you out the Z. And if that's the case, and I'm using my right hand, that's a right-handed coordinate system. Usually it's just right-handed right-handed system. If you want to mess with people, you could do it a left-handed way, and X and Y. Okay, so it's across that way, but if you take your left hand, it comes out at you. And so this is a left-handed coordinate system. Throughout physics and stuff, that doesn't work very good. So they don't like those. There's only one place I've ever seen that, and that is there's this CAD program. I don't want to say the name of it, but years and years ago, they started back a long time ago, and they started as a 2D program. And, you know, that's what CAD started as, a 2D. You draw your dots and your lines, and you make a part and stuff like that. Then suddenly 3D came along. And what they did is they said, well, depth, so, X and Y like that should give you a Z at you. But they gave it the other way. And so they used the left-hand coordinate system in their CAD program for a while. It propagated itself to the point where It went into the 3D, and only about 5-6 years ago did they make the default right-handed again. And it really messed a lot of people up, because when you take the stuff out of their CAD and move it into the other, it would sometimes take the image and flip it backwards. And so usually the book, I'm not sure if it's listed like this. Most of the time, I like to list it like that because you're used to drawing X and Y, and the natural extension is to have the Z coming at you. So sometimes in the book, they may put, X and Y and then Z up, but that's okay as long as you know that, and the right-hand rule will tell you what the coordinate system is. Once you've got it, your coordinate system that is, then you're starting to look at it like, okay, I need to find vectors. A is equal to AX, I, AYJ, and AZK. Now, there are a multitude of sections in there. The book has them very tightly compacted, so they're really quick and easy to go through. But the first one, I believe the first one, is where he does projection. And the nice thing is since we've been talking about projection already, that's the reason I wanted to go here first. So let's say you had a vector, and I'm going to put numbers to it in a second. So here's some vector A. Now, as it turns out, if you put the sun up here, and it's far enough away so that it creates a straight line shadow, it might project a shadow onto the ground, essentially a projection onto the ground. It'll look kind of like that. So imagine it like Drakeley noon. You have a tree that happens to be leaning off like that, has no branches on it, it's just a stick. I've got one of those in my yard where the thing cut it over, and I cut a lot of the limbs off, and so it's just sitting there. At certain parts of the day, I mean, I don't go out there, but at certain parts of the day, it'll basically, the shadow will move. So you're looking at high noon. So let's say the magnitude of this is like 10. And then say you went out there, this is kind of unnatural, but let's say you went out there and you measured the angle. And you found that it's unnatural because usually you don't generally measure angle. You measure more often distances, and then you figure out angles. But let's just say it was 30 degrees. And it hit the ground, and so at that point, you could look at the shadow, okay? Same thing here, okay? The sun was up here. It basically made it so it was high noon. This high noon, or 90 degrees, same thing here. So it's high noon, 90 degrees. Now, in the book, he has this way of doing this. He'll make this triangle like kind of a light shade of blue. And then what he does is he says, okay, now that I found that, that's nothing more than 10 cosine of that 30 degrees. Same thing here. The high noon here basically means you standing there, you look straight up past the tip of the vector, and you see a light source coming down. That makes it 90 degrees. So, of course, you could have a shadow that did like this, but that's not a projection, and that's not what cosine will get you. So now that I've done that, I got to get that off of there. So the next question is, now that I've got that, now you have to decide on the ground which direction. Okay, so if you got this, okay, so you got this coordinate system sitting here. Okay, I guess I'll have to stand here. Your thumb is this way. Okay, well, I can rotate around that Y to the point where X and Y. So you have to decide which way is X. And so we're just going to decide because it was decided for us because I drew the thing. And now let's just say this is 50 degrees, just for lack of anything better. And what does that make that one? So you got 40 degrees. Now, as long as I can, I'll use different colors. Okay, so this part's easy because it's basically straight across. However, let me do this. I'm going to make Z go down a little further so that I'll have room to make this go across. Now this line, and guess what? I got to make that go further. How about that? So what I'm going to try to do is take this thing. This is good enough if there's straight edge, and just sort of slide it across to the point where it basically does like that. And so once you've got that, then you got a vector this way and a vector that way. And those are easy enough to figure out. Okay, that's the length of this vector projected through 30 onto this axis. Okay, that's a little thing here. It may not look like it's 90 degrees on the board, but you can kind of visualize if you were rotating down that the reason that is the case, the reason it's 90 here and 90 here, is already it was decided that that was 90 degrees here. So all these are separated by 90 degrees. In other words, y-axis is 90 degrees from the x is 90 degrees from the z. Even though it doesn't look like it on the board, you know, we're in a perspective kind of view. So in fact, the fact that that line and that line are 90 degrees means that all these are 90 degrees. That's 90 degrees and that's 90 degrees. And so you've got this new vector. The x component of the A is the projected vector. The sunlight projects it onto the ground. So it is of length 10 cosine 30. But then I project it onto here from across the 40. And then I do the same thing over here. So that was the AX. I'm going to have to erase and make that extend too, but that's okay. This is the AZ, which is the 10 cosine 30. Why? Because it got projected on the ground, and now I'm going to kind of project it onto this axis. And then I've got to multiply it times the cosine of 50. So that's that one. And now I've got to make this go up. So now I'll go ahead and get rid of this. Oh, I guess I should have kept that, but well, that kind of tilted off there to the side. So I got this vector right. So I just have to slide up here and do a halfway reasonable job of copying that so that this, in fact, is a plane. And that tells you that this is the AY component, which actually is two ways you can look at it. I always look at a projection or the other one. If it's not projecting, it's the other one. So it's 30, so you can say 10 sine of 30. Or you can come through and say, okay, I'm projecting through this angle, and the sunlight's coming this way. It produces a shadow that goes right up that axis. What's the angle it projects through? Well, what's 90 minus 30? It's 60. Okay, so that's nothing more than 10 a cosine of 60. So again, the way I look at things in your math, many years ago, they had a theta, for example, and they had hypotenuse, opposite, adjacent. So they did cosine of theta is equal to That doesn't look like an A. Is that an A? That's here. Oh no, wait. Make it like capital A. And then that's already a little O. I just imagine that's a capital one. A over H. Here I'll make it H for hypotenuse. So, and then they did the sign. Okay, so in my mind, that's two things to remember. If I can just remember sunlight and projecting it down, I project this H onto here through the sunlight. It's like this. So to me, I can just remember one thing, and then I can remember the other. And so anytime it's not projecting, and I'm supposed to use the non-projecting angle, I go to sine. So I think that way. So in essence, you'll see this in the book. This is exactly what you see in the book. However, I don't know whether he has it listed X, Y, and Z, or whether he has it listed X, Y, and Z. I don't remember. So you can think of that, okay. There's a reason you can rotate, okay, X, Y, and Z, right? So this is the right hand. But then you can move this to X. And if you do that, you're just rotating them right through it. Or you can move the X here, the Y here, and the Z here. So you think about it, he's either going to have one of these. He's going to have either the X, Y, and the Z, or the X, the Y, and the Z. And if this is the X, you swing it into the Y, and it should point to the Z. If this is the X, notice I put them in squares or circles or non. If this is the X and this is the Y, you take your X, swing it to the Y, and your Z will point that way. So there's this thing what they have where it's this funny rotation. If you rotate your X to here, then you take your Z, you rotate it to there, and you take your Y and rotate it to here, and you'll still have a right-hand coordinate system. So you can represent this three different ways. I don't know which one he does. For some reason, my memory serves me, if it serves me right, I think he has X, Y, and Z, which is okay. It doesn't really matter. The plot is the same. The plot being that what happens is you have a plane. Actually, you have this whole thing as a plane. But in there is this vector A, and it gets projected onto the ground. And then it gets projected onto that axis, and then it gets projected onto that axis. So you got this weird equation that ends up like this. A is equal to, and that's given that I've projected it this way. You can project it with different coordinates, like I said right there. You can say the X component. Let's go after the X component, which is this. 10 cosine 30, and then cosine 40, I. And instead of writing it all that way, I'm just going to do it this way. Then I'm going to do the Y. Okay, so I like cosines better, but I guess I better use the sine. 10 sine of 30j, and plus the last one, which was this, 10 cosine 30, and then cosine 50, and that would be k. So the key is you had two projections. You had one projection which was projected again here, and projected again. This one was special in that you basically could just draw it straight across because somebody told you the angle there is 60 in this particular case. So does this all make kind of sense? Now, he does a better job of color coding this. Here's what he does. He makes this little triangle here kind of a light shade of blue, and then this triangle is like, because really, you don't need both this triangle and this triangle, because the length from here to here is the same as the length from here to here, right? So he draws this one as kind of a darker shade of blue, I think. Either one's dark, one's light. Anyway, there are two triangles he focuses on. This one and then this one. And that's what he's doing. So just imagine it's a projection. Okay, so if you're okay with that, I'll move to the next thing he does, which is really strange. And so, and I'm going to start working problems next week, but we got to have this material and actually to kind of do that. So the next thing he does, are we okay? Is anybody, yeah. What,
Why is the projection onto Y special?
why is it? Well, basically because, here's the reason. It was given to you as the 30 degrees was from the angle to the ground. So the fact that you were given that, you could, in other words, flip it all around so that the angle would be given from this vector to this plane. Does that make sense? And then, okay, so imagine, okay, so here, let me redraw it. I'm not going to redraw the same thing, but I'm going to try to. Give me a second. I'm not even going to put an X, a Y, or Z on it. So there's a vector, right? Now what I did before is I took the sunlight up on Y, so I took the sunlight way up, and then it's way millions of miles away, and it shines down on the ground. Now I'm going to take the sun. It's not natural to do this, but I could take the sun way out this axis. So the sun's way out of here. So here are the rays of light, and suddenly it produces a shadow on the wall. Did I draw it? I didn't. I did draw an arrowhead there. So I produced this as a shadow on the wall. So since I produced it as a shadow on the wall, the sunlight was coming down this axis. And in the same way, I hope this is making sense. In the same way, the sunlight is coming down down the y-axis. So that makes the y-axis special because it forms, let me see if I can do a good job of this. Okay, so what I did is I took the projection, right, that got on the floor, and I moved it back. Let me use my very expensive ruler. And so what I did is I took the projection, moved it to the tip. I take the projection. This is unnatural. This one's more natural. So I take the projection, move it to the tip. Now, it sounds weird, but let me finish this out before it might make sense a little bit better. Okay, take that. Now this is going to be weird. I'm going to ask you to do something in a second. Okay. Now, you got to take this one. Okay. So essentially, I got this vector. It's looking weird, right? It's looking very strange. So say this is, I'm just making this up. Maybe this is 60, and maybe this is 30. But this is forming a plane right there. So maybe the angle to the ground, maybe that's 45. So you got to project it onto the ground. Now, if you want to get a perspective of this, turn your head sideways and look at it for a minute. I mean, literally, if you turn your head sideways and look at it, it's like, oh, it starts making sense to you. But you have to kind of line your brain up so this one's vertical. And if you do that for a minute, and you're like, oh, okay. But then you turn your head back to this one makes sense if the sunlight's coming down. The human brain is so weird. I can show you some videos that, and maybe we'll do that later when we have time, that makes you realize your perception is very, not very useful sometimes. You can easily be fooled. Let's put it like that. And your visual perception is the best place to fool a person. This is an example of that. And it takes you a minute, And this is on the video stream, so if you want to go look at it on the video stream, pause the video, turn it sideways, and look at it. You can turn. Some people can turn their monitor sideways. If you're looking at it on a tablet, if you turn the tablet, sometimes the tablet shifts too, so you have to freeze your tablet so you can do that. But in fact, if you turn your head and you look at it, you're like, oh, okay, so I get it. The light is coming, projecting this on the ground. This is 45. Let's say it's 40, just to be strange about it. Say it's 50. And this angle, because guess what? This is 90 degrees here. So I'm doing this, turning my head because I can see it a little bit better. And so this becomes okay, let's do it like this. This is a plane. And every one of the angles, well, this one definitely is 90 degrees. You look at it for a minute, if you were able to move yourself this way and look up at it, but you can't do it because it's on the board, but if you could look up at it, you would see a box. And so if you saw this as a box, you're looking up at it and you're like, oh, okay, so this axis is, I didn't say the dimensions of here. What did I say it was? Say it's 10 long. 10 long. And since this is projected through 50, it's the other one. That becomes sine of 50. So that's what makes the Y so special, is the shadow. The first shadow is shooting down the Y-axis and projecting it on the ground. If you want to have your brain twisted, you could have it projecting this way. Am I making sense there? Does that make sense? It's kind of weird, but you have to turn your head a little bit. Does that make sense?
That one makes more sense than that.
Yeah, it does, but if you sit there and you turn your head and you stare at it for long enough, and you get over the fact that you're turning your head, you can kind of see it makes sense. If you want to stand up here and turn your head and look at it, you're welcome to. But I may have to take that board space in a minute if that's okay. But it's on the stream if you want to go look at it. I think it's on the stream. Is it? Yeah, it's on there. Hang on, let me. Yeah, you could do that. Yeah, so go look at that, turn your head, and you'll see what I mean. But yeah, it's special in the fact that the shadow is cast upon the ground here. That means that this is a box. It doesn't look like a box. But if you were like able to get over to the side and look at it from this angle, which you can't because it's 2D, I'm projecting it on a 2D, you would see that that's a box. Those are all 90 degrees. That 90 degrees, that 90, they're all 90 degrees. And so once you see that, you're like, okay, I get that. So I'll go ahead and go to the next thing that bothers people some, but then this whole concept of dot products. Now I'm going to do something very bizarre. I wish I could just copy this over to the right, but I'm just going to write it and try to do the best I can at it. And so here we go. I got my 10. There it is. It comes down like this. And I'm just halfway doing this part. So you got your vector right. Here's your vector. It kind of, here's your shadow. Here's your thing. Here's your vector here. Here's your vector here. And here's your vector here. So you get this being AZ, this one being AX, this one being AY, and this is the A thing all together. So I did this without the purple line, without the black line, I did put this as a dotted line. This is a dotted, or dashed. This is dashed. So they're kind of there, but you see the main ingredients. Now there's something weird you can do. Okay, let me make sure I get there's my X, there's my Z. I got to make sure I get these right. Okay. Now, I got this vector. I got that vector, which is a K. I got this vector, which is a J. Let's make sure I got them right. I goes along with X. J goes along with Y. K goes along with Z. Okay, so we're all good there. Now we have to get out of this plane and get completely into 3D space. And we have to do this. Okay, let's take our vector A. We're going to dot it with something. And it's going to be the magnitude of A times the magnitude of I times the cosine of the angle between them. I'll call that alpha. Now this is just the standard. This is the reason you should do, I think in the book, you should do dot products right off, because then you can start seeing this. Okay, so you look at this for a minute. Well, okay, what is dot? How can that be represented here? And of course, I'm going to have to erase a few things here, and I'm glad I got some extra colors. First of all, you already knew this, and you knew this from the minute, because we talked about this before. The length of that's just 1. So really, you got the magnitude of A times the cosine of the angle between it. If you're looking at this, what is this? Not from the right side, but from the left side. Okay, AXI plus AYJ plus AZK is that vector. This is that right there. I'm going to dot it with I. What's I dot J? Nothing. I dot K? Nothing. I dot I is just 1. So you get this. And then you're like, oh, hey, you know what? If I could turn around and do this, and I'll do this on these, I'll figure out these numbers in a minute. Or maybe I'll get you to figure it out, because I'm terrible with the calculator. So now, you find out that so think about this, and we talked about this last time. Think about this. I want to find a unit vector that runs along here. I'm going to call it unit vector A. What should unit vector A look like? Unit vector A should look like A, the vector, divided by A, the magnitude, right? So what's that going to be looking like? It's going to look like this. AX over A, I plus AY over A, J plus AZ over the magnitude of A, K. Oops, sorry, that's a K, sorry. So you're buying into that? I mean, that's what that is. Stare at this one, and then stare at that one, and then tell me what goes there. What can go there? What is there is right, but you can represent it a different way. You can represent it like that. And you can do that because you took the dot product with this thing. Now, we figured out this and this and this. And what we're going to do is I'm going to tie this one back to this one in a second. What do you think happens if I dot the vector A with J? And this time, say alpha, beta, this one's beta, and then the other one's gamma. They line them, they do them that way. You'll see this exact thing in the text. Now, my gammas look like that. His may have two bottom, maybe closer together, I don't know. Gamma's indifferent, depending on how you typeset, different textbooks will change the way the gamma looks a little bit. That's the only one that really is bothersome. So guess what you get? cosine beta j plus cosine gamma k. So this, in fact, is a unit vector. If you had this, and if you had that, and if you had that, you can enter. Now, what is that? Now, this is where it takes a different type of mindset here. If you take two vectors, any two vectors, any two vectors, just put your hands out any particular way, you're forming a plane. That plane, so if I take my two vectors, point them like that, the plane is like this. Any two vectors drawn any particular way will form a plane. They actually, believe it or not, I wish I had bigger, they actually don't have to touch, but if they do touch each other, it makes it easier. I mean, you can take any two lines, but you know they're going to come back together and touch somewhere. So you might as well make them touch. That's what's happening here. So if I take this vector A, and then I take that one, the AX, I've formed a plane. I can pull it. So maybe this one's sticking out of the plane. Maybe this one's not. And suddenly I pull it out and look at it. I say, oh, wait a minute. I'm looking between the two, angle between these two. So what you're doing, this is not in the plane of the board. This is alpha. This is beta. And this is gamma. Now again, this one actually is represented back here, and we'll show you that that actually is what that is. And when we go through the math. But in fact, that's the only one that's straight up because I made the sunlight go down this axis. So these are, the fact that I made that sunlight come down this axis means that this beta is actually this value right there. But this alpha and this gamma is not anywhere on here. There's nowhere on here. And so let's go about the process of taking this problem, figuring out the numbers. Okay, so can y'all help me figure out what this is? Okay, A is equal to one number times I plus another number times J plus another number times K. And so this one and this one and that one. If you could do 10 times cosine 30 times cosine 40, what's that equal to? 6.634. What's this next one?
5.
Oh, 5. Okay. What's that one?
5.567.
Okay. And what we're going to do, okay, someone gave it to us this way. The sunlight went down. We went out in the yard, and we were funny. We measured this angle. We got this. However, more than likely what you're going to do is you're going to have the length of the tree, and then you'll go out and measure the shadow, and you'll back out the angle. But that's neither here nor there because you're going to usually have a, as a matter of fact, I've got a thing, everybody has that on their iPhone, that measure thing where you can measure things, So let's see if we can let's first find the beta. Okay, before we find the beta, what do we have to do? Here, I tell you what, I need some space. Actually, I can just erase this now. So now I want to find the unit vector in the direction of A, which will equal 6.634. Now I'm going to find the length of A right up here. Square root of 6.634 squared plus 5 squared plus 5.567 squared. What's that equal to? I have no idea. Say 4, 10. It's got to be exactly 10 because I ran us through a barnyard. I made you calculate that again, sorry. My mind slipped there for a minute. It should have been just 10, because I made it to be 10. I'm sorry. I didn't mean to make you work for no reason. So that's 0.6634 I plus 0.5 J plus 0.5567 K. Let's go after this one first. Okay, now what I've got, and you got to stare at this and think about this, I've got the unit vector that I created here. I have the definition of the unit vectors here. So I can do one-to-one. I can take this and point at that. In other words, that and that one are the same. So 0.5 cosine inverse is equal to beta, what's that angle? I hope it's 60. Is it? I'm going to take a drink while you're... Is it 60? Oh, good. Now, let's do a visual here, and this is part of the perception. Okay, let's go with the X. Okay, I know I go down 30 and I sweep over 40. Okay, so if I'm going down 30 and sweeping over 40, just your gut, what should it be? Could it be a 90? Could it be, man, so the question is, what is the angle between this vector and that one? I sweep through 30 to go down, and I sweep across 40, but it's not either 30 or 40. So let's see what it is, and that's this one, the cosine inverse of 0.6634, and that's the alpha right there. So what's the alpha equal to? Okay, 48.44. And if you look at that for a minute, it kind of makes sense. I mean, if you were able to, I know this sounds weird, let's see if I can maybe visualize this. Let's say you take this vector and you take the one on the ground, you're sweeping up. So as you're sweeping up, you're increasing the angle between these two by sweeping up. In other words, it's got to be, because you're coming up, it's got to get further and further away. It just happens to only go 8 degrees more. Does that make sense a little bit? And for that matter, if you're sweeping this up, it's probably 50, 60 degrees swept up to here, because it's 50 on the ground, and as it goes up, in other words, if you took this vector and froze it so it rotated it around, it would rotate it around this axis. It'd still have to go back a little bit. So they're trying to sell me a car insurance. And this is the gamma. What's that one equal to? Like 57. 56.17. Now, let me ask you this question, okay? So let's say I just decided to give you these three angles. Could I give you 60 and 50 and 60? Would that be legal? Are these three angles intimately tied together? I really am not free to. Okay, here's why. If you look at this, this, by definition, is a unit vector. It was created as a unit vector, which means the magnitude has to be equal to 1. So if I looked at the magnitude, I said, okay, the magnitude of this is 1, and let's say I can take the square root of 1, that's fine. So it turns out, and this you should think about for a second. So if I'm looking at the length of this vector, and these are the components, that squared plus that squared plus that squared, and the square root should equal 1. But if I know they're 1 already, I can remove the square root sign and just say that squared plus that squared plus that squared all together have to be 1 to ensure this is a base vector, to ensure that all this works fine. Does this make sense? So when you do that, you're saying you cannot randomly move these around. So imagine this, if I took this vector and I just decided to get it closer to this plane, what did I do? I just moved it down a little bit. Well, what I did when I moved it down, I got it closer, the angle between here and this line and here became less, but this one grew. So there's a really tight relationship between these three angles. They can't be just willy-nilly. They've got to be, they've got to be tied together. So does this kind of make sense? So you've got, this is kind of weird, and this is why you should do dot products first. You'll find that in the book, we'll do this, he'll just blah, this equation out, and he'll just go blah, there's that equation, blah, there's that equation. And then you're like, I'm not sure where that came from, I'm not sure. He kind of does a rough explanation, but if you go to dot products and you use that dot product through the whole thing, you can see where everything came from. And it makes sense. You can get it a little bit easier then. So I got this whole spot. I got that whole spot. I need 2 cameras. Can you do 2 streams at once? I guess you could. That would be hard to watch. Has anybody ever watched 2 YouTube videos at the same time? I guess if you had 2 computers, and then you'd have to get them in sync, because then it would be an echo. Do what? Oh, there you go. Well, that's one way to do it. Well, no, wait, but it'd still be one. Well, I guess you could launch 2 YouTubes at the same time, and just.
The way I had it is I had one where I game one I watch YouTube, and the other one I look stuff up on.
Oh, really? And you don't interchange them, huh?
No.
Oh, you don't? Oh, okay.
They're all the same thing, and they flow together.
Oh, okay. Well, I hope this makes sense. Does it make sense? Am I making sense? I mean, sometimes I make sense to me, but then I can rattle off endlessly. I've been intrigued as of late by watching some of, oh yeah, we're done. Okay. I'll talk about that later. I'll show you some videos a month or so from now. Yeah, tell me if I'm going too long. I don't want to spend more effort than I need to.